Yeah, okay. Thank you. You can start your session now.
Okay, so thank you so much to Albedo Foundation and all the participants for for joining this session. I think Vikrant, you need to allow me to share my screen. And thanks a lot for the introduction. I will. Okay, I can share my screen now. I hope that my screen is visible to all the participants.
Yes, it is visible.
Okay. Yeah. So yeah, I've already. Yeah. I think we are past the time for starting this session, and I will take you guys through the use of AI in climate science, the past, the present, and the future. So this is a paper from where we will start. See, so this was published in 2015. These are the European Center for Medium Range Weather Forecasting scientists. It's the best forecasting system in the world, and this paper was published in 2015. Now, uh, so 2015, they said in Nature Review, the quiet revolution of numerical weather prediction. On the right side, you can see one graph, okay, where you can see the forecast skill, and the top line it shows. So the blue one is for day 3, the red one is for day 5, uh, yellow one is for day 7. So these are the lead time. So this is 3 days before, 5 days before, 7 days before, and this is being shown from 1981. So so from 1981, what what are the what was the skill of the numerical weather prediction for northern hemisphere, southern hemisphere? You can see that the forecasting skill has significantly or substantially improved, and it took about like from 1980s to this is until 2015. So that's a period of around 35 years. It took around more than 3 decades for the numerical weather prediction to reach at a stage where we were able to get skillful forecasts, and that took a lot of investments, lot of science and research has gone into the development of these numerical weather prediction models. Now, after you can see that at some point the models have they have started to saturate. The skill is not it's not going up at that scale or that speed as it was in the past. So then comes the era of the AI in weather prediction. So the first thing that came out, this was a paper which came out in 2019. It was from the University of Washington, Dale Duran and Jonathan Wayne's work on. So they talked about whether machines can learn to predict weather. Okay, and they used 500 hectopascal geopotential height at time t as input and t plus 1 as target. So this was based on, like, this was a very revolutionary idea, and uh, at that time people would not have thought that this would work. So they took a global data. You can see at 500 hectopascal geopotential they took, and they also took the temperature at 850, and they just built an autoregressive system. So that autoregressive system was basically uh, to predict the next time step in era 5 reanalysis. And so era 5 reanalysis has been a great success story. That's the best ground truth that we have. And so here, by doing just so this is a has been taken from from UNet. UNet is an image to image regression algorithm, and they were able to get results which were almost near the ECMWF IFS forecast, but they were not yet there. So the next thing that they did was, in 2020, the same group, they published this paper wherein what they said was that Earth is a sphere. So the advancements in the computer vision have taken place on image datasets, and those image datasets. But if you directly want to use those algorithms to spherical dataset, either we build spherical convolutions or you build spherical transformers, or what you have to do is do something that you can use the image algorithms on spherical data. And they had a hypothesis that their previous model, which was DLWP, deep learning for weather prediction, its skill was below the best weather prediction model, because there were spherical distortion errors. If you project the spherical data on a 2D plane, which is what most of you see as the maps, you would see that the area of Russia or Europe, that is enlarged, whereas Africa looks like smaller to them, whereas that's not the case. So they took a cube sphere domain. So cube sphere is basically four faces along the tropics, two along the poles. You can see, so it has got six faces, and then they basically embedded the spherical data on a cube sphere domain, and they when you open a cube sphere domain, it looks something like this. So these are the along the equator. You have the four faces along the equator, two along the poles, and in a unit, traditionally, people would pad it with zeros. So as to ensure that the input and the target size of the image remains the same. But since this is a sphere, you can pad it with the adjacent face edges. So there is a transfer of information that takes place, and the physics and the teleconnections, global teleconnections, are preserved. What happens because of that is you basically are able to build a system which can actually start to mimic the physics of a system. And then what happened was, these so in this paper, what they were able to do was, they were able to get performance of the at the resolution on which they ran this model, which was as good as ECMWF IFS. Now, these studies, they were basically they did on temperature and geopotential height, but precipitation is a complex field, and what we did was, so the precipitation is a big challenge, and I changed this problem from a temporal problem to a spatial problem. So we took the temperature as a proof of concept from ERA 5 data, temperature at in CubeSphere domain as an input, and precipitation as a target, and used a unit algorithm in between. So we call it modified DLWP CS. This paper was published in 2023. And what we are able to find out is, so this is the data that we took. Weatherbench is nothing but modified. It's just a data set from built from ERA 5, but served to the data scientists to train their AI models. So these are some examples of the fields from Weatherbench. So we took the 1979 to 2009 for training, 2010 and 11 for validation, and 2012 to 2015 for testing. So you can see that this is a median of day one precipitation from ground truth, that is ERA 5. This is from the GFS. So GFS is run operationally in India, in US. It's the operational weather forecasting model. So you can see the pattern of precipitation from GFS. And you can see we built two models, in one in which temperature was input, another in which total cloud cover was input, and precipitation was target. So you can see that both our models, they are able to they look similar to ground truth when you just see the median. Linear regression, it just doesn't show anything. And then when we computed the correlation coefficient at each grid point, so you can see the DL1. DL1 is a model which total. So we have total cloud cover as input. DL2 is the one in which we have surface air temperature as input. So and you can see this is GFS. So the GFS scale, it's between 0.2 to 0.3. For example, over India, the correlation between the GFS and the ground truth. This is from 2012 to 2015. This is the test period. And for our model, this was a proof of concept. Over India, you can see we are getting skill of around 0.6. This was actually amazing. Like even like when we started with this, I don't think we could have believed that it would work so well that we would be able to beat the skill of GFS just with a simple system, just with temperature as input and precipitation as target. And these are the evaluation metrics for the modified DLWPCS for different regions, and it can be seen that for all the major land regions, the model is basically better than the GFS baseline. So then the next thing that followed up from here was whether we can build an actual product out of it. So then came out this work wherein what we did was we took the output of a physics-based model or a dynamical model, which is climate forecast system version 2. That is also running in India and in US. Operationally, it is the model of choice because its skill is really good globally and particularly for US and for India. So what we did was we took the day 1, day 2, and day 3 lead time forecasts of the NWP model CFSV2 for these 3-day lead time. So for surface air temperature and for precipitation, we normalized the data to from -1 to 1 and brought the data into cubed sphere embedding. Same thing we have to do with the era 5 precipitation, which we take as the ground truth. So you take that thing also as you normalize it and bring it in a cube sphere domain. And in the cube sphere space, you basically train a unit and denormalize it and then do an inverse mapping. The hypothesis is that this model should be better than the CFSV2 hindcast. So now I showed in the first slide, I showed the paper on point revolution of uh, numerical weather prediction. Now we are actually trying to improve the numerical weather prediction, and the training data that we took was 1982 to 2000. Validation was from 2001 to 2002, and test data is from 2003 to 2010. So the first thing that we would like to see is how is the performance of the climate forecast system version 2. So the so this is a plot from Mukhopadhyay et al. 2019, wherein they have basically run a data. They did a data analysis. They run this model. They have set up this model, which is CFSV2. It is set up at IITM, and it is all the weather forecasts that you're getting. People think they get from Google, but eventually the data is coming from these models, which is run on the HPC in IITM. And you can see the first image. This is from iMerge. So this is the ground truth, and you can see the day 1, day 3, day 5, and day 8. These are the climatologies from the GFS. GFS T1534 that they are running at IITM, and these are the biases: day 1, day 3, day 5, and day 8. You can see that over important land regions, for example, over Western Ghats, over Central India, over the plains immediately after the Himalayas, there is a bias of over 10 millimeters per day. This is like, and this is the average. This is the average bias. You can see that, and so we have now trained a model. the first thing that we should do is basically evaluate our results with these results. So you can see on the left side is our model. We call it deep NWP, or the deep learning model, DL. And so DL minus error 5, you can see the bias is basically at lead day 1. Over India, over other parts, it's within the range of -1 to 1 millimeters per day. Whereas for the CFS V2, it's you can see it's more than 10 millimeters per day, as Mukhopadhyay et al. Had shown. And the same story repeats for day 1, day 2, and day 3. This is for June, July, August. June, July, August. So we did analysis for different months, because June, July, August is when we have monsoons over India. Basically, most of the rainfall it is in June, July, August. And you can see for September, October, November, same story. And December, January, February, March, April, May. Now we wanted to check whether we are able to see this kind of results for individual test cases or not. So there was a very famous Mumbai heavy rain event 2005, the Mumbai floods. So the floods that they happened on the 26th of July 2005. We got an initial condition from CFSV2 from 25th of July. So 26th July is the lead 1 day forecast, 27th July is the lead 2 day forecast, and 28th of July is the lead 3 day forecast. So you can see from era 5, it's raining quite heavily over Mumbai, maybe around more than 50 millimeters per day. And it's also raining over the central India. Our model, which takes in the CFSV2, and it tries to predict the era 5 precipitation, it's doing a reasonable job when you see the spatial pattern. Whereas if CFSV2, you can see it's raining heavily in Arabian Sea, Bay of Bengal, it's just raining. So there is a lot of false alarm. We can see that there is a lot of wet bias in the model. As Mukhopadhyay et al. Have also shown, the model has high wet bias. It doesn't just have wet bias, it has a lot of spatial bias as well. It You can see it was just raining over the coastal area, but this is raining everywhere in the in the sea. And when we see the bias from our model, so our model minus error 5, you can see it is like it is within some acceptable range, but this CFS V2 for this particular event, this is going maybe beyond 20 millimeters per day. And then we saw there was a cyclone Nargis over Myanmar. So you can see this is the ground truth at lead day 1. This is our so the second one is our deep NWP, and the third column is the CFS V2 output. It's basically the over different cases, even for Hurricane Katrina, Hurricane Ivan, and all these cases, they were not seen by our model. I mean, we trained the data on which we trained our model, it had not seen these cases. So we also saw for China floods, for Central Europe floods, and this is the table for deep NWP and for CFSV2 at lead day 1, lead day 2, lead day 3, and these are for the different events. We were able to find for averages, there was an improvement by around 10 times. You can see from 3.8, it's the bias is going down to minus 0.3. This is global average. Whereas when we see for each event, we were able to get even more than 20 to 30 times improvement. So
Hello,
this is,
Manmeet.
yeah.
Sorry for the interrupting. Actually, we are seeing the maps. So now
Okay,
right
you are
on.
not able to see my pointer?
No.
Okay, let me just
And
see.
not able to see have you just discussed related to your table, or you are discussing related to your maps?
I am discussing the table. Are you not able to
Yeah,
see
yeah, yeah,
the?
yeah. Right now we can see the table. And for the pointer option, can you please go to the options related to pen or something like that in a red color in Zoom only, so we can see your pointer also.
Okay. Just a second. I will. I'll check. Uh, yeah. So yeah, I was talking about the improvement that we were able to get for the different events as well. Now, I talked about in the first slide, I talked about the past, which was the revolution of numerical weather prediction. I talked about like some of the work which was which has catalyzed the development of AI for climate science. I've shown you some of our work. Now, I will take you through the recent developments in pure data-driven AI and WP. So after Jonathan Wayne's work, a lot of interest has been created amongst different uh, tech companies, Google, Nvidia, Huawei. So they have just jumped into this problem of numerical weather prediction, and they have taken the approach of what the Dale Durance group had taken. You take time t as input and time t plus 1 as target, take all the variables of era 5 at all the levels, and the same variables as input and same as target, but make it as a temporal mapping problem. Now, this is a paper from this came in Nature. This is, I think, Pangu weather. It came in July, so it is now 1 year, and they used a 3D Earth specific transformer, and in this work they have basically used positional embeddings, so as to ensure that they take care of the location that is encoded in their transformer. Now the blue one, they this is a final figure from their paper. Blue one is the track forecast of the typhoon. This typhoon was going somewhere in, I think, Southeast Asia. It's from the ECMWF IFS. The red one is the Pangu weather forecast, and the black line is the actual track of the or the ground truth of the typhoon. This is one example, and this is another example. You can see that it's like the AI and WP model. It's as if somebody has just drawn over the ground truth, right? So yeah. So the next thing was there was another model which is called ForecastNet. Now there, so it was released by NVIDIA. I think I don't have ForecastNet in the slides. I have. Uh, I'll go through ForecastNet first. So in ForecastNet, what they did was this model actually came before Pangu weather, and here what they showed was that you can just take all the data as input and all as target. So the Dale Duran paper in 2019, 2020, they had not taken all the variables as input and target, but ForecastNet, they have taken Fourier transform on the spherical data. So they train in the Fourier space, and they show that you can get results which are as good as the actual RA5 data. And after ForecastNet came Pangu weather, and this paper is the revolution. Now this is Google's GraphCast. So what they do is they embed the spherical data, which is which is over the Earth, as a graph. So it is taken as an icosahedral grid. So at M0, you can see this grid is basically like an icosahedron, which has like 1, 2, 3, 4, 5. So it has 10 faces. Okay, and for going from M1 to M2, what you just have to do is you have to you have to create So you have to divide each triangle into four different triangles. So you just take the midpoint of one edge, midpoint of another edge, just join them. So this is one triangle, then this is another triangle, and this is another triangle, and the center one becomes the fourth triangle. So from you go from M0 to M1, and then similarly you can divide each triangle in M1 into four triangles, go from M1 to M2, and keep going. So they took up to M6, and you can see that now this icosahedron is approximately a sphere. It is now you are not doing that kind of crude approximation, as in you're not considering the earth to be a cubed sphere, but rather you are considering it to be a graph where each node, this is a node in the graph and this is the edge in the graph. So the machine learning is basically, so the neural networks are trained on the graph. So there is a graph in and a graph out for all the variables, and then they develop it in a way that you input a weather state, predict the next state. Now if you can develop this model, you can basically roll out a forecast. You can just give the predicted state to the model, you can give it back, and you can get the t+2 you can give it to the model and you can get t+3. Now GraphCast, it is the best. Okay, I'll just show these results. So these are some results from as a comparison of the different AI and WP models. You can see Pango Weather, GraphCast operational, Pango Weather operational. So I want you to see the precipitation because that's the most complex field. So on x-axis we have time at 1, 3, 5, 7, 10 day lead, and the RMSE, root mean square error of GraphCast, is these numbers, and the color, it represents how far are these different models from IFS. IFS is the ECMWF weather forecasting system. So you can see that at lead 3, 5, 7, 10, GraphCast is actually beating the IFS precipitation forecast. For other variables, it is already better. Like that is something which it has which other models have also like there are these other models, they have also performed well, but you can see that GraphCast, it is able to show skill even in precipitation. Now that was something huge, and yeah, so GraphCast is the state of the art, and then but the results have been shown up to day 10 lead time. There is another model which has come out from this is from a Chinese university, I think somewhere in Hong Kong. It's called Fushi model. So Fushi, they take the cube sphere embedding, and in the cube sphere, after cube sphere embedding, they take a U transformer. So they take time t-1 and t as input and t+1 as target. So when they build it in this way, they are able to get the results which are like for other fields. For example, when you compare Fushi with GraphCast, Fushi is even better than GraphCast at, let's say, at up to 10-day lead time. But the thing is that these other models, so not every model has got precipitation output. The ForecastNet version 2, they have got precipitation module, so you can get a precipitation forecast from them. And then this is the next frontier. It's called Neural GCM. So Neural GCM, what they're doing is they basically replace the entire physics in an Earth system model with a neural network. And they've shown that you can run this model for an year, for 10 years, decadal simulation, you can do climate simulations. So all the climate modeling, this is the future of climate modeling. So uh, like I anticipate that in the next IPCC reports, we should be able to get AI or system models which would participate in the next assessment. And yeah, this has shown skill which is much better than the existing CMIP models. So next I would come to from global to weather prediction. So I'll talk some slides. I will talk about our work. So this is a tool that I developed. So which I call as downscale bench, and this paper was published in 2023. Now the global models, their resolution, for example, GraphCast resolution is 0.25 degrees. People run models at maybe 10 kilometer, which is or 9 kilometer, which is considered as a very good model at a global scale. But you might have seen that even within the cities, there is much variation in the temperature, in rainfall that takes place. So we need to basically do super resolution or downscaling. And to do that, there are a lot of challenges. So where would you get your source input from? Where would you get your target high resolution data from? So super resolution doesn't need a high resolution target. They basically, if you read the original Dong et al. Super resolution paper, they would do a forward mapping, forward by linear interpolation, backward, and then a backward. So bring it back to the same resolution. And once you do this forward and the backward map, you lose information, and that becomes your course resolution data. So and then the model is basically a general purpose operator which can do mapping from any resolution to any resolution. uh, you have to select a scale factor. It can be 2x, 3x, 4x. So in our downscale bench tool, we also have the facility to incorporate station information, the course resolution input, high resolution target, and it basically builds a supervised learning data set for a user, so that they can train a high resolution data product or data model for their region of interest. Okay, this is the iterative SRCNN. I'll not go much into the details. I will just show you the final product. So we went from 10 kilometer, that is not shown. So that the 10 kilometer JAXA rainfall GS map rainfall product. We went up to 300 meters. So we have developed the 300-meter gridded data set of rainfall and temperature over Austin and over Delhi. And this is available for the past 20 years. The next thing is, we call as climate downscale suite. So there are a lot of different super resolution algorithms. You can go from a low resolution to a high resolution, but these models are in the computer vision community. People in the climate space, they have not been using these models to the extent that they should. So we have developed in a single collab notebook. A user should be able to use these models very simply. They should be just able to change the data and use these different models. So you can see that the transformer based models. So in the bracket are the PSNR values, the peak signal to noise ratio. What we did in this work was we basically mapped from the VIRS. These are the nighttime lights data. So the VIRS is taken as input, and DMSP is taken as the target. So DMSP stopped in 2012, and VIRS it is available from 2012. So taking 2012 as a baseline, we have developed this tool which is called Climate Downscale Suite. But the thing is, our experience with this downscaling algorithm, it says that like you won't get good results if you don't incorporate station information into the downscaling. So we have developed this novel architecture for downscaling. We call it as Meteogan, in which the generator can be any super resolution algorithm. You pick it from Climate Downscale Suite, and then the discriminator, it can be anything like VGG19, VGG16, and the input of discriminator is a high resolution map, and the target is the station data. So you're basically minimizing the loss over the station information, and then you are doing a forward and a back prop. to get the best product or the best high resolution map of the credit data. We have these are the results from Meteogan on over Delhi. So this is one test case that is shown. So this is chirps at 5 kilometers, and then we have bicubic interpolation at 300 meters. You can see that there are these two blobs. This is one heavy rain event over Delhi, uh, which was which we also saw like greater than 150 millimeters per day. And you can see that there are two blobs of heavy rain. One is over south of Delhi and one is on the east of Delhi. Bicubic interpolation, it has just, it has just spread out both these blobs. But Meteogan, you can see it is preserving the distinctness or the uniqueness of these two blobs of precipitation. And we are able to see rainfall, like the spatial variation is much more visible in Meteogan. And it's not just spreading out the information. Bicubic is just, it is just like linearly or in a bicubic manner, it is spreading out the information. And this is over another event, which is for Delhi. And then uh, I so the next thing is Meteogan. We have been working on Meteogan for the land surface temperature. And uh, so this is an example over Austin. So we have been able to build 30-meter daily land surface temperature product, gap filled product. And the input of this, we are using the different physics based data sets, like the water mass, the trees, grass, the built up area. Just as a at a very shallow level, you can see that wherever you have trees, you can see this is over the north of Austin, northwest of Austin, you have a lower land surface temperature, whereas where you have this built up area, where you have high urban area, there is the temperatures are much higher. And this is just a city, okay, and this is like from 97.85 degrees to 97.65. So just a zero point 0.2 degree by zero point 0.2 degree box. So just 20 kilometer by 20 kilometer. Now in a global model, this would be a global model is like of for example, if the model is 0.25 degree, which is GraphCast, this would be just represented by one single number. And you can see that how much is the variation in the temperature. Over this point, it is going maybe above 40 degrees Celsius. And in the same city, it is even, you can also see like 20 degrees Celsius. So there is a difference of 20 degrees, and that would be represented by just a single number. So that would not be useful for the real operations or for real world applications. Now coming to future, what is the future? The future is in diffusion. Now diffusion is a big concept in LLMs and natural language processing, but it is also showing great promise in uh, in the uh, in the computer vision world. So so what we do is you basically add noise to the data. Okay, you iteratively add noise. Let's say sigma equal to 0 corresponds to zero noise, but at point 2 you add like, so 20% of the data is noise, 80% is the actual data. When you reach sigma equal to 50, it actually looks just noise. What we do is iteratively, like you build a denoiser. So from noise at point 2 as input and 0 as target. So so uh, so uh, you build a denoiser iteratively. So from point 0.5 to 0, 1 to 0, 2 to 0, and it will work like magic. And diffusion is everywhere. Okay, so everything has diffusion in the societies, in the physics. in the air, water. So the model is basically, you can say it's like a physics inspired deep learning model, and you add diffusion to any model, it will improve. So the idea is, so in this paper what they have shown is, you build this denoiser. Okay, you build this denoiser first, then compute the values over the station data. Okay, and you have the station observations, get the loss function over the stations, backpropagate the loss, improve the denoiser. Now, in this way, you can build a data simulation system using diffusion, and your model that you have can be the same thing that you started with. You can do super resolution with this. You can do anything. Yeah, we are also working on heat related. So how would the behavior of society change? And this is a work that we are doing on estimating the hotspots of heat anger index, where people are getting more angry because of heat. This is using large language models and climate based information. And this is very important because heat is becoming a big problem. People are dying because of heat. And the agencies, different agencies over different locations, this is over US, they need to know where to take intervention, or where to go and take some steps, so that people can be, they can take some actions, so that heat mitigation can take place. There has been a lot of work on GPTs for remote sensing community. This is the future where GPTs need to come to climate. And yeah, there is this paper, they have proposed an Earth and Climate Foundation model. This is not yet built. There are a lot of chunks and pieces that need to be built. One is building autoregressive Earth system models. So GraphCast and ForecastNet and Pangu Weather, they are for atmosphere. I am building the similar models for ocean and for land. All of you are most welcome to join, and like, if you would like to lead a research component, take that lead. Most welcome. And I'm building this autoregressive ocean model and also land model, similar to what GraphCast, ForecastNet, and Pangu Weather have been built. And eventually, it is going to be a lot of AI in climate science. And I have tried to cover from the past, the present, and where we are heading to for AI in climate science. Thank you so much for your time. It is always a pleasure to talk on this topic, which I'm very passionate about. And I hope to see you guys in future. Somebody who would like to do research with me is most welcome, and I'm happy to take any questions if they are. Thank you so much to Vikrant and Albedo Foundation for organizing this session and webinar. And it is always a pleasure to be a part of and to give talks on the platform of Albedo Foundation. Thank you.